So let me start by reminding you the general system, right? Okay, so I want to get some sort of mean field limit for a system that is like this. Okay, and that's what I called in general the strongly non-exchangeable systems. And so the next example is when you already have some underlying structure on the Wij. And so this is very, very simple. Well, let's assume that to each agent, we can assign a state. Psi I, right? So to agent number I can assign a state psi I. Psi I is, in some space omega, and let's not be too precise about what omega is. You'll see actually in the end that you can always take a very simple structure for omega. So this doesn't really matter much. All right, so I can assign a state psi I such that the Wij is simply some function of psi I and psi j. Okay, very, very simple. Now, why is this possible? Well, in general, you might ask, there's no particular reason for it, but of course we can think of some cases. If I'm going back to the examples of biological neurons, what you find, and this is again has a long history starting in the late 60s, actually. You find in the literature various assumptions that the way two neurons are connected may depend actually on their physical location. So Wij depends on the physical location of neurons number I and neurons number J. So then, of course, psi I is just where the neuron sits in the brain. Right? So it's location. So it's something in R3. Okay. Now, as I said, there's a long distinguished literature that is based on this assumption and that derives continuous model based on this assumption. And I'm not going to dig into it, that would take far too much time. If you're interested in that, that particular field, the field that developed around that assumption, has a name, and it's called neural field equation. That's all well and good, but this is also something that has received its share of criticisms, and the criticisms in particular are based on the fact that the assumption is essentially not true, in the sense that it's relatively easy to find in the brain neurons that are very, very close by and that have completely different connection. Um, all right, but this gives you an idea of the type of one potential reason why we may have an underlying structure like this. And now this has an immediate advantage, right? Assuming you can be in that framework. Because now basically what we have, at least as long as K is smooth, again, we are back to the cases of section 2, meaning what we have is really a classical system provided that we add the psi I to the state. Right? So I can define a zi, which is, bigger vector xi, I, where zi dot is, of course, equal to, very, very importantly, sorry, it should be one over n here that I forgot. I'm going to come back to just now. And I have a new system. And I have a new system which has the form of a classical many-particle system, identical many-particle system, with a new interaction current. Right? Instead of having k of x, xi, xj, now my new interaction kernel that I'm going to call k bar of zi, zj, right, has the following form. Very, very simple. And what you see here is this completely and very naturally extend the case of the weakly exchangeable system that we had discussed in section 2, right, relatively at length on Tuesday, where W psi xij is just xij. Right? So we're good. If K bar is Lipschitz, then I can apply the classical mean field theory, and it works. And what we find as a limit is an interesting extended Vlasov equation. So now the limit, of course, because I'm working in the extended phase space, right? The limit is not just on f of t and x, it's on f of t, x, and psi, right? So I need to find, and I need to look at the limit, the one particle distribution, not only in x, but in x and psi. So this is a new Vlasov equation with a modified kernel and an extended one particle distribution. And at least things now start to be interesting because we have as a limit something that is not the same as the Vlasov equation for identical particles, right? Because we see now a trace of the connection maps between the particles or between the agent at the limit on the Vlasov equation. So we are very, very happy with this. Now, a certain number of comments following this very straightforward idea. First off, all right. If k bar is not Lipschitz, right? We may have problems. And here again, I'm going to refer to our discussion on Tuesday, right? Where you saw that outside of the case of Lipschitz interaction, sometimes going to the extended space was breaking some of the symmetries of a problem, and this breaking of symmetries was preventing us from using some of the known methods, right? And the same thing can apply here, right? If you don't give me Lipschitz interactions, then I might have problems going to use other methods like relative entropy or modulated energy for the same reasons. However, we can refine this remark a little bit in the following sense. The key is that k, right, k of x, y is Lipschitz. And that's because you see that in the system, right, the psi I are given, they are fixed because I don't have time dependent weights here. So psi I are given once and for all, they don't evolve in time. And so what they do is they really play more of a role of a parameter here. And so if you're really trying to do Gromov estimates, right, the type of things that you're doing for classical mean field approach on the empirical measure, for example, you don't have so much problem with psi. And so you don't need that W Lipschitz. And it's the same at the level of the limiting equation, right? You see that psi and zeta here really just play the role of parameters. There's no derivative in psi or zeta in the equation. So you need less regularity in psi and zeta. So for W of psi zeta, continuity is more than enough, and you can even deal with less, right? This is something that we'll talk about in section 4, less than continuity. right? But for sure, if W side zeta is continuous or Holder, right? Then you're completely good. You're completely out of the wood, and whatever you were doing before, you're going to be able to apply it here. So that's that's very very important. You actually don't need that much. Now, of course, here the third remark, what f of t xi, or the initial data, right, is depends. So if you give me a deterministic psi I have to put Dirac masses. Depends a little bit, okay? But if the same psi is being repeated for a lot of particles, for example, then I might actually have a Dirac mass in psi in F0 at the limit because I'm not using that many of them. If you throw the psi randomly, then it's different. And this leads me to a fourth point, right? The psi is in implicit parameters. This is going to play a major role in the rest of this presentation. So I'm going to take 2 minutes here to explain in detail what I mean by that. What we care about is not F, right? What we care about is the real initial one-particle distribution, which you can recover by taking f of t x psi and just integrating in psi, right? Assuming that I don't have Dirac masses or I don't have measure in psi, otherwise this is a bit of an abusive notation. So this is the object that we care about. And so very, very obviously, I can reshuffle the indices, I can reshuffle the psi in this equation. Right, so everything is invariant over measure preserving transform. Let's assume they are bijection to keep things simple here. You can do much crazier than that. Right, so what I'm saying is I can do a transform, right? So I can have a phi that is going to go from omega to another space, omega tilde, right? To psi is going to apply phi of psi, which is psi tilde, right? And I can assume that phi is 1 to 1 and is measure preserving. Okay? So whatever measure you have on omega, which might not be the Lebesgue measure, and whatever measure you have on omega tilde, which might not be the Lebesgue measure, right? Then the push forward of 1 by phi is the other. And then I can change variables, right? So now I can define so something like this, right? Just change the tilde here. So that I don't have to work with phi minus 1, if you don't mind. So f of t phi of xi tilde, right? Then, of course, and I don't change x, g d xi tilde, and again, please replace the Lebesgue measure by whatever measure you have on omega tilde if you want, is the same that f d xi. And I can do the same change of variable in the equation. So G satisfies a similar Vlasov equation. So K doesn't change, W changes, right? Where, because now I have to use the phi. Right, so I'm going to take the equation on F and I'm going to write it at the point phi. And I'm going to have this G y zeta y t zeta. Okay. So let's call that W tilde xi tilde zeta tilde. And it's the same form. So you have a huge amount of invariance in this equation, right? That give the actual same one particle distribution after you integrate into the implicit parameters. So this representation, when it exists, is never unique. You can always change it. And because of that, right, as long as omega is a Banach space with a measure, or even a metric space with a measure, you know, I can use the very famous result that says that all those spaces are isomorphic to the interval 0, 1 with a Lebesgue. Of course, that may affect, however, the regularity of W. So you might still not want to do that, right? Because if I have a W that is very smooth on R3, right, in the neural for a neural field model, for example, and now I'm trying to do a measure preserving transform from R3 to 0, 1. Well, that measure preserving transform is not going to be by Lipschitz. Obviously, you cannot have a by Lipschitz function from R3 to R. So you're going to lose regularity, right, when you combine W with that measure preserving transform. So you might still want to work with a bigger space omega where you have a nice smooth W instead of going back to omega equals 0, 1 and have a crazy W. Okay. And a last remark here that I'm going to be relatively quick with. In that particular framework, there is also another interesting notion outside of the mean field limit, which is called the graph limit. Now, the graph limit is an attempt to use the extra parameter to actually get the limit on the trajectories themselves. And so one way to do it here is to define something like that. A capital X of t small x and psi by gluing together the various trajectories. So I'm going to take the limit of the piecewise function where I'm taking xi of t and x, right, where I'm starting xi at point x. And for example, the indicatrix function that psi is close enough to psi I. So if the psi I are well distributed, for example, you can do something like that. Psi I plus 1 over n, right? Assuming that you have a distance, a correct distance between the psi I. Now, I'm really not going to elaborate that much on this because I won't have the time. This is interesting, again, because you have a sort of more precise limit than what the mean field limit is giving you. The mean field limit gives you the one particle distribution, so if this is a statistical object, the graph limit already gives you something on the trajectory, so it's more precise. It's also something that is relatively constrained because, for example, I cannot really take, not with this simple definition, I cannot take random initial conditions. And if I take random initial conditions with this, then, well, nothing survives at the limits. So I would need to do something much more complicated if I wanted to have a graph limit with random initial conditions. And it's basically the same reason that you cannot just glue together several Brownian motion, take the limit, and get anything interesting, right? That's not how you construct a white limit. All right. Now, for all of this, and in particular for this framework, there has been a recent preprint by Paul and Trella that I'm going to refer to because it's super complete. So there's everything there that you want to ask, and probably a few things that you didn't even think of asking. So if you have this structure that is given to you, and if the W has some minimal regularity, I think they have to assume continuity, then they will tell you everything you want to know. All right, so this is, again, another fairly straightforward example where we end up being able to reuse a lot of the tools of the classical theory. And what we're going to try to do in the remainder of this class is get as close to this example as possible. And so now I'm going to jump to section 4 and just do a bit of an introduction, and then we'll continue after the break. And I want to discuss graphon theory. Okay. So graphon theory is something very, very famous that was introduced by Lovash about 20 years ago. And he has a very nice book that I highly recommend. And it's something that tries to derive the limits, the large-scale limits of graphs. And so it's a very natural way of trying to solve our problem, right? Because of course, what I can see, I can always interpret the Wij as weights on a directed graph. Right. Directed because Wij is not necessarily equal to Wji, right? So the weight in one direction might be different from the weight in the other direction. Fair enough. And here's what Lovash says in a nutshell. Lovash says is the following. Assume that the wij now have the scale 1 over n explicitly. Right? So I'm going to make it very explicit by rescaling them. And the w bar ij are order 1. And we are going to construct an approximate graphon. Which is going to be a kernel function of 2 variables, right? So exactly like the kernel I have here in my limiting equation with the structure. And the way I'm going to do this is I'm going to do that inspired by the graph limit. So I'm going to take 0, 1 square, right? And I'm going to cut it into squares of size 1 over n, right? And I'm going to build a piecewise object that at, you know, part I and part j puts wij bar. So if you want a math formula, this is something like that. It's, psi is an I minus 1 over n, I over n, and zeta is an j minus 1 over n, j over n. Then w bar n is uniformly bounded in L infinity. And here is an incredible theorem. I can reindex, or I can perform a measure preserving bijection. So let's write it like that. There exists phi n, a measure preserving, such that the wn bar after reindexing, so after you apply phi n, is compact. And it's compact in the space, which is the space of operators from L infinity to L1. L infinity of 0, 1 to L1 of 0, 1. So after extraction, W bar of phi xi, phi zeta, converges strongly for the topology again of seeing them as operator from L infinity to L1, converges strongly to some W psi zeta. And we find a structure. At the limit, we find an underlying structure when nothing was present initially. So this is completely miraculous, right? From a lot of point of view. And of course, it is perfect for us. Although then there's a bit of work trying to put this into the framework of the mean field. and I'll comment on that after the break. So there's still a bit of work for us, but this gives us the promise that the previous example, right, where we had an explicit structure, is actually going to be generic, at least for the Wij whose scale like 1/n, is going to be generic because we are always going to be able to bring ourselves back into this. I will stop here so that, you know, we still have a reasonable break. And I'll take a few questions if you have them, and otherwise we'll continue.
Okay.
After
Yeah,
the break.
is there any question from the audience? Yeah, maybe we take a half an hour break.
Yep.
Okay, yeah. Thank you. Yeah.
All right. So let's take still half an hour, right?